More limits. Section 1.3, now we're dealing with what happens if. So let's kind of show you an example here. First example, we learned the other day, or the last time, that direct substitution was our favorite way to figure something out. So if I do directly substitute here, I would get a 1 minus 1 in the denominator, or a 0. And everybody knows, I hope, at this point in their mathematical career, that you can't divide by 0. That just doesn't work. It would be undefined. It would be something along those lines. Well, I'm here to tell you today that limits in no way can ever be undefined. A limit can't be undefined. This is no good. So since it's no good, we need an alternative. So what we're going to have to do is we're going to have to try some of these things that we have listed in these goals up here. Factor and cancel, rationalize numerators, dealing with trig. Okay, so here's what we're going to try instead. So since direct substitution didn't work, I'm going to get this out of here, and we're going to say, let's try this instead. Well, what could I do to change this function without really changing it? Well, it looks like that numerator is actually the difference of 2 cubes. So let's rewrite this limit as x approaches 1, and let's try factoring that difference of 2 cubes. Well, let's see. I've done enough of these before that I know that this is supposed to be an x and a 1, and an x squared and a 1 squared, and in the middle a 1 times an x, and then my signs are always the same, the opposite, and then always positive. And in the denominator, I already had this x minus 1. So now when I look at this new limit, well, gosh, look at that. My x minus 1s are going to drop each other out. If they drop each other out, I have the limit as x approaches 1 of something that now has a 1 in the denominator, which means my direct substitution is going to work. So now if I try my direct substitution, I've got 1 squared plus 1 plus another 1. This limit is going to exist and is going to actually be y equals 3. So one of the things that I do if I can't do direct substitution, is I try to factor and cancel and then try it again. A second thought. Well, what happens with this second one? Well, this second one, obviously I can't substitute a 0 into this denominator, no good. So my direct substitution is going to be what we call an epic failure. So if that doesn't work, now what I'm going to have to do instead is change this equation. Well, notice we've got a radical in there, we've got a quantity there. If you think back to algebra and trying to deal with radicals and move the radical, we're used to rationalizing denominators. What we're going to do here is we're going to try a little technique that we call rationalize the numerator. Well, Mr. Perkins, you said before that you didn't care if we rationalize square roots off of denominators. No, I don't. But what you're going to find here, rationalize is another word for move the square root from one level to the other. Well, here we've got something that we can't substitute into. So let's multiply by this conjugate. So the conjugate of root of x plus 1 minus a 1 would be that same root of x plus 1, but this thing plus a 1. Remember, when you choose a conjugate, you're always trying to create a difference of 2 squares situation. So if I go and do that, let's rewrite this problem. So how about limit as x approaches 0 of, let's see, numerator. If I multiply out those two binomials, the first term in the numerator would be a plain old ordinary boring x plus 1. The outside terms when I multiply them by would be a positive 1 root of x plus 1. The inside terms would be a negative 1 root of x plus 1, thereby making the outside and inside terms drop out. Negative 1 times positive 1 minus 1. In the denominator, I want you to fight the urge to distribute that x. Let's just leave it as it was, because there's really never a need to multiply out a denominator, and you'll see why in a second. So if I go and do this now, well, let's see, let's simplify. Well, we still can't do direct substitution because this 0 can't be substituted in and place that x. So what I'm trying to do here is I'm trying to get that x off the denominator, because if I get it off of the denominator, then the direct substitution will work. So in the numerator, let's see what happens. Well, look at here. Here's a positive 1 and a negative 1, so they're effectively gone. So what's my numerator really? Let's take this thing, and instead of rewriting the problem, I'm just going to erase this numerator, and let's just put a plain old ordinary boring x there, because that's all that's left. And if I do that now, well, look at here. Here is that x I wanted to get rid of on the bottom with the x I have to get rid of on the top. Let's leave a 1 up there in the numerator. And if I do that, what I really have is the limit as x approaches 0 of 1 over the root of x plus 1 plus another 1. Will direct substitution work now? Can I put this 0 in place of that x and get a result? You sure can. In fact, I think what you're going to find is you're going to have, pardon me, a 1 on the top, and on the bottom, we're going to have the square root of 1 plus another 1. How about those? That limit will exist, and its result will be y equals 1/2. So second technique, rationalize the numerator. What about when we get down here and we start dealing with trig? So with trig, here's what's going to happen. You'll notice with both of these limits, regardless of how we have them written, the first one and the second one that's written two different ways, limit as x approaches 0 in both of them, and direct substitution isn't going to work because that 0 can't go in that denominator, and nor can it go in either of those denominators. So what we're going to do is we're going to try to work our way around it. Special trig limit, this is what's going to happen. The limit as x approaches 0, sine of ax over ax. This quantity has to match that quantity. If that's the case, this limit is always 1. No questions asked. If you want to prove it to yourself, punch in sine of 2x all divided by 2x and graph it and take a look at what happens when x equals 0. And I think you'll see the two sides of the graph coming together at y equals 1. These other limits, limit as x approaches 0 again, of these two things, it could be written both ways. These limits both come out to be a 0. And again, notice you've got to have that 1 minus cosine of the same ax here that is there. Those two things have to match in order for these limits to fit. So what do we do with number 3? Well, number 3, tangent of 4x over an x. Well, first off, do we fit this description? No, not really. We don't have a sine. We don't have a cosine, but we do have a tangent. So direct substitution isn't going to work. I've got limit as x approaches 0. I've got an x on the bottom. My first thought would be, what would be nice is if we could have a 4x in that denominator. So what I'm going to do, little algebra technique, let's multiply the bottom by a 4. Well, is that legal? Well, as long as we also multiply the top by 4. So rewriting this equation, limit as x approaches 0 of 4 times the tangent of 4x divided by a 4x. So now we're getting there. I wouldn't say we're really close yet. But now, I wish I didn't have tangents in there. Well, if we wanted to change it, well, let's see, tangent is the same as sine over cosine, so let's rewrite this thing. Limit as x approaches 0. How about instead of tangent, let's do 4 sine of 4x over cosine of 4x, and divide that by my 4x. Well, let's see. So what did that do for us? Well, let's rewrite again. I've got a fraction divided by 4x. So let's change this up. Limit as x approaches 0 of 4, let's just leave that a plain old ordinary boring 4, sorry about the quantity, times a sine of 4x over a cosine of 4x. And if I'm dividing by this fraction 4x, then that would be the same thing as multiplying by 1 over 4x. Well, now let's get a little creative, because our special trig limit says sine of 4x over 4x is that's our pattern. There's our special trig limit we have up there. So let's rewrite this problem. Limit as x approaches 0. And let's kind of change the order of how we multiply things. Let's make it sine of 4x over 4x being multiplied by 4 over cosine of 4x. Well, let's see. The blue thing is your special trig limit. So if you figured out the limit as x approaches 0 of that thing, you would end up with the number 1. If you look at the black part, limit as x approaches 0, well, what is the cosine? Well, wait, 4 times 0 would be still 0. Cosine of 0 would be 1. That would mean if I did the limit as x approaches 0 of 4 over cosine of 4x, I'd have really 4 over 1. Multiply those two things together. What's that spell? I've got a limit here of y equals 4. So third technique, when things break down, if you can't do direct substitution, try to change your equations around using some of those cool identities we learned in trigonometry and see if I can make a special trig limit or direct substitution, or in what you're just looking at right now, a combination of the two.